Log on, tune in, find out. Another good idea from Cambridge.
Montpellier and CNRS, and we will talk about nonlinear coherent states and Ehrenfest time or Schrodinger equation.
Thank you. So first, I'd like to thank the organizers for this invitation here. And what I will present is a joint work with Clotilde Fermagnan from Paris. And I will start by describing the expressions that are used in the title. I will just first present coherent states and what I mean by Ehrenfest time. I will not be too precise about the constants, and then switch to the nonlinear case. Okay, so the equation I'm starting with is the semi-classically scaled linear equation, Schrodinger equation. So V depends on x, could depend on time, would change nothing in the analysis. I will state the assumptions on V later on, and V is real valued, and we are interested in the limit epsilon goes to 0, but I will not consider WKB initial data. More precisely, the initial data I consider are semi-classical wave packets. The features of such initial data is that they are concentrated in space around x naught, the initial position at scale square root epsilon, and in frequency around xi naught at scale actually square root of epsilon 2, because you have to think that the right variable is x minus x naught divided by square root epsilon, so there is one square root epsilon left. So it's concentrated in space and frequency at the same scale square root of epsilon, and that's essentially the best you can do if you are in view of the uncertainty principle. And so unlike what happens for general WKB initial data, there will be no caustic phenomenon in the propagation of such initial data. Well, one of the reasons is that the plane is, the phase is linear with respect to x. So I will not be too precise about the regularity of the initial profile A. So it's Schwarz class. You can think of it as a Gaussian, typically. Okay, so as I said, it's concentrated in space and time and frequency, and the Wigner measure can be computed explicitly. It's a delta in x and delta in xi, and Christophe will be more precise about that tomorrow morning. Okay, the assumption on the external potential, so it's smooth, C infinity, real valued, and it grows at most quadratically in x. So meaning that every time you differentiate it twice with respect to any variable, you get something bounded. So the typical example is the harmonic oscillator, isotropic or anisotropic. It's not important, but you can think of, well, it can be linear. When it's a polynomial, as explained this morning in the talk by Caroline Lasser, you have many explicit formula without errors. It's exact formula. We will see that if, in that case too, if the potential is exactly a polynomial, then there will be no approximation. We will construct an exact solution, but otherwise we will have an approximate solution. So I just write the Hamiltonian system associated to the Hamiltonian xi square over 2 plus v of x. And under these assumptions, we have a global solution, which is smooth, and we have an exponential control. When I say exponential control, I mean that x of t plus xi of t grow at most exponentially in time, like that. And I mean, if you think of V as a harmonic oscillator, you will say that x of t and xi of t are bounded. So this is not sharp. But if you think of V as a repulsive harmonic oscillator, meaning you change the sign of the harmonic oscillator, then you will have hyperbolic functions, and the exponential growth is sharp in that case. So since I make no assumption on the sign of V typically, you cannot do better than that in general. Okay, so I just introduced the classical action, that's what it is, and I change my unknown function C epsilon to U epsilon. So, so the first guess is we keep a wave packet structure localized at the point x of t in space, so given by the Hamiltonian flow, and c of t in frequency, and there is this s of t which depends only on t, not on x. And okay, since the exponential is nowhere 0, this is perfectly invertible, and the equation for psi epsilon is equivalent to an equation which is no longer in the semi-classical scaling for u epsilon, so if there is no epsilon in front of derivatives, the presence of epsilon is just in this potential v epsilon, whose formula is given there, which in general does depend on epsilon. So it's pure, it's computational, there is no trick there, but you recognize the first terms of a Taylor expansion of v about the point x of t. So there is this 1 over epsilon here, which is singular, but if you think that the next term in the Taylor expansion, it will be of order epsilon, epsilon will simplify, and v has a limit as epsilon goes to 0, which involves the Hessian of v at the point x of t. So in the limit, v epsilon goes to a quadratic potential in y, exactly quadratic, so a time-dependent harmonic oscillator. Okay, so naturally, the approximate solution that we expect for psi epsilon is given by the same formula as before here, but just I have replaced u epsilon here by the expected limiting equation. So I pass formally to the limit in the equation, and I get this time-dependent harmonic potential. So, and this is the most natural candidate for an approximation. Okay, and so to connect with what Caroline said this morning, if v is a polynomial, my Taylor expansion is complete on the previous slide. So this is, there is no extra term in the Taylor expansion, there will be no y cube. So if v is a polynomial, phi epsilon is equal to psi epsilon for all time. So no approximation there. And q does not depend on time because it's the Hessian of v, which is constant. Okay, so the question that will lead to the definition of Ehrenfest time is what happens when v is not a polynomial. So set w epsilon u epsilon minus u, the error, because the scaling is L2 unitary, well, that measuring w epsilon amounts to measuring the error between psi epsilon and phi epsilon, the initial functions. And okay, we just subtract the two equations. So we have that. And I said that u epsilon is w epsilon plus u. So there will be v epsilon times w epsilon. And then there will be some v epsilon minus v times u. So that means we consider we have removed from the Taylor expansion of v about the point x of t, we have removed the first three terms. So the quadratic term is here. So the remainder will be of order controlled by y cube. And because there was a square root of epsilon, we have the square root of epsilon here. So what we can prove is that this guy there in L2 grows at most exponentially in time. So yeah, time will be positive from now on. And well, sometimes you cannot do better than that. In general, it's really exponential. If you think of a repulsive harmonic potential, it will indeed grow exponentially in time. So energy estimate. So you multiply the equation by W bar, integrate with respect to x, take the imaginary part. This guy vanishes because v epsilon is real valued, and the error estimate says that the L2 norm of W at time t is controlled by the integral from 0 to t of the L2 norm of r epsilon, so you integrate an exponential, it's still an exponential, and you still have this square root epsilon. And this guy is small, provided you consider time which are bounded by some constant, not any constant, times log 1 over epsilon. So this is what I will call Ehrenfest time, even though the exact definition of Ehrenfest time does depend on the constant C0 here. I will not be precise, because if I try to be precise at the linear level anyway, I will lose any precision when I switch to the nonlinear case. So, there's been a lot of work done around this approximation for scalar equation, but only for the matrix case. So I would just cite some names, not all of them. So now I switch to the nonlinear case. So I have just changed my equation by introducing some nonlinear term here. And unlike in this morning's talk by Gadifievich, the sign here is a plus sign. That is that the nonlinearity is defocusing. There will be no collapse with that sign. For fixed epsilon, we have global existence in reasonable spaces, so no finite time blow up. So we will be interested in the long time propagation of semi-classical wave packets, like in the linear case. So, but now it's nonlinear. So there is another important parameter which we must take into account, that is the size of the initial data. Because for a nonlinear equation, if you think of really tiny initial data, you think the nonlinear effect will never show up at leading order. So I have just considered the same initial data as before, but there is this epsilon to the kappa, which is supposed to measure the strength of nonlinear effects at leading order. Okay, as a matter of fact, I like to stick to initial data which do not depend on this kappa, and since the nonlinearity is homogeneous, I just rescale every one. So the size actually shows up through the dependence of the complete constant upon epsilon. So this alpha will be 2 sigma kappa. And so the initial data are just the same as before. So heuristically, if alpha is very large, we should get the same asymptotic as in the linear case. When alpha is 0, well, I will not tell you anything because I have no clue what happens. There are extremely strong nonlinear effects at leading order. I have no intuition about the phenomenon in that case. So, but I will show that there is a critical threshold for alpha and describe the critical phenomena in that case. So I resume. So since we expect that for large alpha, we see no nonlinear effect at leading order, we keep the same scaling and examine when it ceases to be valid. Okay, so the same thing as before. It's from psi to u is bijective, so the equation for psi is now equivalent to that equation for u epsilon, initial datum independent of epsilon, and we see here some power of epsilon, and naturally you expect if this power is strict positive, you can forget the nonlinear effect at leading order, and passing to the limit we get the same equation as in the linear case. But when this power is 0, well, you just pass to the limit to the potential like before, and you still have this nonlinear term. So the critical value, natural critical value, is 1 plus d sigma over 2. Now, passing to the limit in that equation, we distinguish two cases. If alpha is larger than this critical threshold, then we get the same equation as before. So I want to emphasize that it's the linear approximation. But otherwise, I just pass to the limit in the potential, and the nonlinearity does not move. And we have this nonlinear envelope equation. And same remark as in the linear case. If v is polynomial, so it's polynomial of degree at most 2, because it has to grow at most quadratic, then there is no approximation in what I have done, at least there. Okay, so what can be proved, I will not insist on that aspect, is that if alpha is larger than alpha c, then indeed it's possible to prove that the linear approximation is a good approximation for psi epsilon up to time of order log 1 over epsilon, like in the linear case. So now I focus on the critical case and investigate what happens. So first we have to understand the behavior of the solution to that envelope equation. So now it's a nonlinear Schrodinger equation with a time-dependent harmonic potential. So I made no assumption on the sign of the Hessian of V. So this potential may be negative, positive, may change signs. We know nothing about it. So this contribution is nice in terms of energy. I mean, if you write the energy when there is no external potential, it's that, and it is conserved. So what is it? So if you construct a local solution in H1, the conservation of this energy gives a global a priori bound in H1, since also the L2 norm is conserved by standard arguments. So, okay, the sum of two positive terms is constant, so the first one is bounded, but when you introduce this guy here, it need not be positive, it may be extremely negative, unbounded from below. So it's not completely obvious that the solution is global. So sigma is H1, so I can rewrite sigma as the space of functions which are in H1 with one momentum in L2. So this is essentially sharp because of the harmonic oscillator that rotates the phase space. So if you have some regularity in X, you have to have the same regularity in C, because they will be exchanged instantaneously. So, okay, if the nonlinearity is energy subcritical, we have a global solution. So, but this is not enough to prove, this is not always enough to prove the validity on Ehrenfest time scales. Okay, a word, well, I will be fast about that. A word about the functional framework. If the nonlinearity is L2 subcritical, then we can do everything in L2. Otherwise, we have to work in sigma. And, okay, maybe a word about these operators. They are nice operators that have some geometric meaning. If we want to derive H1 estimate on such a guy, if you differentiate it with respect to X, so you will have a 1 over square root epsilon when you differentiate U, and a 1 over epsilon when you differentiate the phase, so which is something very singular in the limit epsilon goes to 0. So the most singular is the 1 over epsilon. So what do? Before differentiating, we multiply by the conjugated phase. So when we differentiate, we just differentiate this U. The price to pay is that we lose some square root epsilon. Okay, so this operator has a bit natural meaning. That is, we want to just evaluate the derivative of U, forgetting the phase. And then you say that if you want to evaluate the momentum, you have to remember that you're located about the point x of t at scale square root epsilon. So this is the natural momentum operator. Now, these operators, they are quite natural because up to the semi-classical scaling of coherent state, you rescale everything at scale square root epsilon. It's exactly the gradient and x in the moving frame. That is, you change the center in phase space. So at time t, the center is at xt xt. So you really remember that you expect to have a wave packet centered at that point. Okay, so the result, the finite time approximation, is you set the expected approximation, and then if you set t, any t independent of epsilon, the approximation is of order square root epsilon. And in L2, okay, if the nonlinearity is C2, then you can work in the previous space H. But the error is of order square root epsilon like in the linear case. And something which is a bit frustrating is, so phi is defined in terms of U which solves a nonlinear envelope equation. So there are nonlinear effects which show up in the approximate solution phi, because U solves a truly nonlinear equation. But still, since this is a wave packet, semi-classically scaled, the Wigner measure can be computed, and by conservation of the L2 norm, it's exactly the same as what you would get in the linear case. So you know that nonlinear effects cannot be neglected at leading order, but the Wigner measure misses that. So, okay. So now the question, same as in the linear case, what about t depending on epsilon? How far can we go in the justification? Okay, so in the linear case, I have used, without proving it, the fact that for the linear profile grew at most exponentially in time in space, momentum, and derivatives in L2. That's what I really used. I used that for alpha of length 3 and beta equals 0. But since it's a harmonic oscillator, every time you demand some regularity or some momentum, you have to demand the same thing on for the dual variable. So this is why it's really mixed between x and derivatives. So what we really need is something like that for the nonlinear profile. So unfortunately, it seems proving that from the nonlinear equation is not straightforward at all, and we could only prove it in several cases. So the most satisfactory case is 1D case, d equal 1, and cubic nonlinearity, sigma equal 1. So 1D cubic, we can prove that if the initial datum, say, is Schwarz class, then all derivatives and momenta grow at most exponentially in time. This we can do it. The technical result is this is the only case where the nonlinearity is smooth and L2 subcritical, because, well, the machinery hidden behind the proof of that proposition is Strickhardt estimate. I have no idea how to prove such a control without Strickhardt estimate. Okay, so there are two other cases essentially where this can be established, is when Q of t, so maybe I should rewrite the equation for U. So it's that one. So if Q of t is diagonal with non-positive eigenvalues, so that's the opposite sign compared to the classical, the standard harmonic potential, the confining harmonic potential. So it's a repulsive harmonic potential. And in that case, this will be true and this will be sharp, because there is even more than global well-Posners. There will be even scattering, meaning for large time we can actually forget the nonlinear term. Or if Q is compactly supported, so I recall that Q of t is the Hessian of V along the classical trajectory. So this may happen if you have a compactly supported V, or Hessian of V, with some trajectory that escapes the support of V in finite time. So this could happen. Very unlikely, so that's why I prefer the first 1D cubic case, which is more satisfactory. So yeah, as I said before, it's a bit a pity to be able to prove this property only in these cases. I expect it to hold in a more general framework, but could not prove it. Okay, now we can go up to large time, large as epsilon goes to 0. Arbitrary large time in a way. So in general, I mean, say if Q is compactly supported, for instance, we cannot prove better than a log 1 over epsilon instead of a log 1 over epsilon in the linear case. So we lose some log. So that's quite a lot. But there is one case which is really the good case, because we can prove the exponential control for the nonlinear profile, and we can prove that the approximation is valid up to some log 1 over epsilon, so same order of magnitude as in the linear case. So we cannot expect reasonably the approximation to be valid on larger interval. Okay, so I said I consider only the defocusing nonlinearity. For focusing nonlinearity, there has been similar results, but for specific initial data. So my initial profile A is any function in the Schwartz class. So in a focusing case, A has to be considered as the ground state, which has stability properties, so long time stability can be studied but it will be more using WKB IDs than coherent state. In the case of a non-local nonlinearity, so you replace this power with a convolution, so modulus of u squared convoluted with some kernel k times u. So it's a Hartree nonlinearity. There's a recent work by Athanasoulis, Paul Pezzotti, and Pulverenti in the case where the kernel is smooth. So, and the results are fairly different. Qualitatively, the behavior of the nonlinearity is very different. Okay. So why are wave packets used in the linear setting? Because every initial datum can be written as the superposition of initial wave packets. So what is used, the idea behind is for linear equation, you can superpose initial datum and superpose their evolution, and then it matches the solution of the initial problem. You have a superposition principle. For linear equations, it's obvious. What about this case? I mean, what if we start from initial data which are sum of two semi-classically scaled wave packets starting from different points in the phase space. So it's nonlinear, so superposition should not hold. So a word about the functional framework. In the space capital H which I introduced, I said there were some operators A epsilon and B epsilon which had a precise geometric meaning, that is, you follow one wave packet along its center in phase space. But here you will have two wave packets evolving, so well, you have two family of operators, so you cannot choose one, because if you have a lot of information about one wave packet, the information for the other will be very lousy. So you are ready to lose precision. So I said I don't want to use the gradient because of the phase. I pay a 1 over epsilon. Well, okay, I have no choice. I will pay this price. That's all I can afford. And you say, well, this one is located at point x2, but this one at point x1. So we just control the decay at infinity very loosely. We lose the information that wave packets are concentrated at scale square root epsilon. So we just forget the scale square root epsilon. So we lose a lot of geometric precision, but we have to. So now the result is, I didn't say what gamma is. Yeah, okay, for all gamma less than 1/2, so we do not get quite the same rate as in the case of one wave packet, but think that this contains L2, we say that psi epsilon at leading order can be approximated by the sum of the nonlinear propagation of each wave packet. So the same as if the equation was linear, even though we know that the nonlinear term here shows up at leading order in the envelope equation. So there are nonlinear profiles. Trajectories can cross, but when they cross, they interact, but they don't have time to interact sufficiently, so the interaction appears at leading order. So at leading order, there is no interaction, no nonlinear interaction. Okay, and if d equal 1, okay, and sigma equal 1, so 1d cubic, which is always the nice thing. And we have to make this strange assumption that the energies in terms of the Hamiltonian are different. So this assumption is a bit strange. It's unnatural, but the proof, well, you will see on the last slide, the proof heavily relies on this assumption. So once more, like for the exponential control, maybe it's just better because we have not been sufficiently clever to remove this assumption. But it's unnatural, but we cannot do without. And in that case, we can prove the nonlinear superposition up to, for the 1d cubic, up to log 1 over epsilon time. So we have Ehrenfest for one wave packet, a nonlinear superposition for two wave packets. Okay, maybe I can give you a hint if you don't know which question to ask. What about 3? It will be much more complicated. Okay, so just the outline, the key elements of the proof, and I will give a few details, but hopefully not too much. Okay, if d equal 1, we can get by plain energy estimate. But the outcome is we prove approximation up to log 1 over epsilon. If we want to push the approximation up to time log epsilon, and in other dimension, we need Schrodinger estimate to prove eventually, to use eventually a Grunwald type argument, which is a bit hidden because Schrodinger estimates make all the computation a bit more technical, but the idea is really Grunwald lemma. Okay, the source term, that is the error in, so the approximate solution solves the equation up to some source term. The source term will be essentially the same as in the linear case. That is the third momentum of the approximating profile. So, but now the profile solves a nonlinear equation instead of a linear equation. On finite time interval, we have all the a priori estimates that we need, and for large time, we have a priori estimates only for the approximate solution, so we just use a bootstrap argument. So long as the exact solution remains sufficiently close to the approximate solution, then it satisfies the same estimates up to changing the constants. So now the error estimate that we really get, so in general, it will be a double exponential, square root epsilon double exponential Ct. So this is small only up to time log 1 over epsilon. That's where the log comes from. And in a 1d cubic case, there is only one exponential like in the linear case, so that's why we can go up to log 1 over epsilon. So that's the general picture of the proof. So just a word about Schrodinger estimates, even though I will not enter into details, but we have everything here. So here is my semi-classical Hamiltonian that generates a unitary group, and thanks to the work by Fujiwara, who was studying Feynman path integral, we know that locally in time, this guy has dispersive properties, so it decays like 1 over t to the d over 2. There is an epsilon here, but the important point is that this delta does not depend on epsilon, and proving that is not trivial at all. So what Fujiwara did actually was to construct the parametrics for u epsilon, and it's a byproduct of his result that we have this. So if you think of the case v equals 0, you can prove that by scaling, by just changing x to x over epsilon and t by t over epsilon, and that's what you get for free, because when v equals 0, you have the explicit formula for the group. But since here it's v of x and not v of x over epsilon, a scaling argument is not enough to prove that, so that's why you really need the work, the precious work done by Fujiwara. So we have the same dispersive estimate, and okay, I just write what a Strickart estimate is. I will not really use it more than that. So now I set the error. So I don't change the unknown like I did before. I stick to psi epsilon and phi epsilon. So I still now I keep my semi-classical scaling. I have this L epsilon, which is the error in my Taylor expansion, so the same as in the linear case. I have this guy, which is the reason why there will be some Grunwald type argument. So you have to think that this guy is linear in W, because the nonlinearity here is locally Lipschitz. Okay, so this term, which is the error in the Taylor expansion, involves a third order momentum, and now there is the scaling, but up to the scaling it's the same as in the linear case, but I have replaced U-lin with U solution to the nonlinear envelope equation, and we have the same estimate as in the linear case. So, and the key is to prove that this guy is controlled exponentially in time. We will have then the same source term as in the linear case, essentially. So the problem will be actually this guy, which we have to control by Grunwald argument. So this is absolutely not funny. Okay, there is algebra that makes Strickart estimate work really nice. So here is what you get in the end. So you have this singular power, but it's not so bad. So I want to control this guy. So I said it comes from this term. So I just write psi is W plus phi, and I replace everyone there. So you have to think that this is a nonlinear potential. But this nonlinear potential, I want to control it. So this term can be absorbed by the left-hand side. And this is where we pay some price. Okay, well, no, maybe I don't want to prove it. Okay, what we have in the end is this estimate. If I consider the time interval, so did I write what I is? So I is some time interval starting at time t of length tau. So what we have, if tau here is sufficiently small, we hope that this guy will be eaten by the left-hand side. So now there is an algebraic miracle. All these awful indices there are chosen, so the total power of epsilon here is 0. And that's a hint of criticality. You can erase all the epsilons. Yeah, sorry. So cancellation, no epsilon left. Now if you choose tau sufficiently small, you can put this on the left-hand side, and you come up with some nice linear estimate. Okay, which is, and then you Strickart estimate again, what you get is something like that. So that's for finite time. So you just split any time interval 0 capital T into finitely many such intervals where tau is fixed small once and for all. So on a finite time interval, it's okay. You do finitely many operations. And okay, what you come up with is that. Then you use, at this stage, you use the standard Grunwald inequality, and you have that. Now you have to keep track of the dependence upon t, and that's the painful step. Okay, I skip that. Why do we have double exponential is that my nonlinear potential in general will grow exponentially in time. So essentially what we come up with is something like that. So the source term is the same as before, but in my integration I have this exponential, which is due to the fact that my nonlinear potential grows exponentially in time, and I cannot do better in general. So once I have that, Gronau lemma gives me a double exponential. There's no way you can do better with that estimate. So double exponential means log 1 over epsilon. Okay, the trick if in 1D cubic case is that it's L2 subcritical, and it's one of the magical aspects of strict estimate that we can get such an a priori estimate. We actually do the same computation as before, and we don't have this exponential there. So we have a simple exponential in the end. Okay, now the main ideas about the nonlinear superposition. So my error is the difference between these three terms. So my nonlinear term is obtained like that. I just subtract the equations satisfied by each equation, by each function. And now I want to split this nonlinear contribution into two parts. There is one, so S stands for semi-linear. So it's essentially, you can see it's the same as before, but I have just replaced phi with phi1 plus phi2. So it's essentially, you have to think this is linear in W. So you can factor out W because the nonlinearity is Lipschitzian. So this will be the Gronau term. But you have to take into account this Ni. I stands for interaction. So that measures the nonlinear interactions between my two approximate solutions, phi1 and phi2. So this is a new source term. So the goal is to check, so there is an epsilon minus 1 here because there is an epsilon in front of the time derivative in the equation. So the goal is to check that this guy, the interaction, which is my new source term, is small. So the idea is that morally, since we consider coherent states, they are scaled. They live about 1 point at scale square root epsilon. So if you think typically that you will have to consider, say, some power of phi1, some power of phi2. So alpha plus beta is 2 sigma plus 1. So you will write that if I multiply like that to some power m, phi1 alpha, so x minus x2 square root epsilon m phi2 beta. So what I have to do is multiply by, okay, epsilon m x minus x1 x minus x2 m. So this is my interaction term. Now I want to use the fact that, okay, it's localized, it leaves, phi1 lives about x1 and phi2 lives about x2. So I just multiply and divide by the same factor. And we get, we get this general result. The question is, can the trajectories cross? In general, yes, they can. They will cross, but as I said before, when trajectories meet, the truth is that the wave packets don't have time to interact. So we will distinguish the two cases. Either the trajectories live in a very tiny neighborhood, so gamma will be between 0 and 1/2, technical, and we distinguish the set where the trajectories are close one to the other at the order epsilon to the gamma, and when they are sufficiently apart. So the distance is larger than epsilon to the gamma, so that's not very big, but that will be enough. So we have two kinds of terms here. So when the trajectories are very close, we essentially do nothing, we just measure the size of this set. But when x1 minus x2 is larger than epsilon to the gamma, I say that I can gain some large power of epsilon, large meaning that k can be as large as I want, provided I pay some price on the regularity of the profile. So you see that here k is very large. So the idea, so to have this estimate is precisely to write what I wrote here. Now what I use is the Petri inequality that tells you that this guy, well, if it's 1D, you can just study a numerical function. But this guy is controlled by so epsilon to the m and x1 minus x2 to the 2n. To n? No, m. Okay. So we have that, and since we are outside of I epsilon, this would be m minus m gamma. Probably made one mistake somewhere, but okay, that's the idea. So when they live sufficiently apart, you gain a square root of epsilon because of the support. But since gamma is smaller than 1/2, 1/2 minus gamma is a positive power. And if we pay a lot of regularity, we multiply this by an arbitrarily large number, so it's as large as I want. Then I just have to optimize between these guys. But now I have to measure the size of I epsilon. So I epsilon, if I consider finite time interval, I can say, okay, that trajectories will meet, but okay, they will meet transversally. So if x1 at some time t is x2, by uniqueness, I necessarily have xc1 different from xc2. So they cross transversally. So since if t is fixed, by compactness and some uniform continuity, the set I epsilon of t will be, the set where they meet is finite. There are only finite times where classical trajectories cross. There will be some uniform continuity giving a nice measure for I epsilon of order epsilon gamma. So now I use my previous lemma, I optimize in k, and I get the result presented in the beginning. So last slide, and that will explain why we have to assume that the energies are different, is that up to Ehrenfest time, we can prove some control like that. So we have an exponential in time, but we already have so many, it's not important. So this guy will be small if we stop at time of order log epsilon. But we have, in the constant, we have the inverse of the difference of the energies. So that's why technically we have to assume the energies are different. So there is no reason geometrically why we would expect this condition to be necessary, but technically we cannot do without. And the proof is 1D. So that works only in the case d equals 1. But okay, there's no reason to expect this to be a typically 1D phenomenon. We believe that it's just technical limitation. The phenomenon should be more general. Okay, thank you.
Why do you know that psi1 is different from psi2 here?
Because if I had x1 equal x2, xc1 equal xc2, then the three trajectories would be the same, and I assumed that initially the wave packets were not centered at the same point in phase, because otherwise it would be just one wave packet.
Yes, but how can you be sure that they are not? You're just trying to derive the estimate now that they will always stay.
What you have to do is use some uniform continuity to say that when they cross, you can bound actually Xi, that is x dot. So you have a uniform Lipschitz constant.
Okay.
So they cannot be in a narrow neighborhood unless, okay.
Next question. What are the hypotheses on the potential V on for Fujiwara estimates?
Exactly the same as I made. Well, he allows time dependence of the
Time dependence.
on the potential. So the time dependence is measurable. So for what he proved, it's locally bounded. And if we wanted to make the potential time dependent, we would demand a global bound in time. I mean, when I So yeah, here, I mean, we would have to demand the same thing with a uniform. I mean, we differentiate only at least twice in x, and it's bounded in space-time. That would be the nice assumption.
So your last slide, this problem with the energies, this is an ODE protocol.
What do you mean? We have to assume that the energies are different.
Yeah.
Yeah.
I mean, this is just purely on the side of controlling the trajectory.
Exactly. Yeah. Yeah.
So this
Yeah.
has nothing to do with
With wave packets, no. It's a Hamiltonian. So you have x and xi given by a Hamiltonian flow, and yeah, okay, right. It's an ODE problem.
It's like an exercise.
You know, when you get old, you're not even able to do exercises.
Well, thank you again.